As a next example, let's look at the following problem. So let's see what the number is. Example 5. So here let f of x be square root of x, and I is an interval from 0 to 1. I'm going to assume that this interval is closed. And I'm asking the same question. So show that f is continuous on I by using the epsilon delta definition. Of continuity. All right, so let's do the following here. So select any x0 that belongs to the interval I, such that x0 is not equal to 0, right? So as usual, we want f of x minus f of x0 to be less than epsilon. And so let's analyze what f of x minus f of x0 is going to be. F of x is radical of x minus square root of x0. I want this to be less than epsilon by making x minus x0 less than delta, so I need to transform this expression to x minus x0, and I can do that by multiplying and dividing by the conjugate. So let's do this. Square root of x plus square root of x0, and we divide by the same quantity. So this will become, right, square root of x plus square root of x0 is positive, so I don't need the absolute value there. All right, so we get absolute value of x minus x0 in the numerator, square root of x plus square root of x0 in the denominator. And of course, at the end of the day, I want delta to be independent of x. So I need to get rid of the square root of x in the denominator. And in this case, I can clearly see that if I just drop it, then the whole expression will become larger because square root of x is a positive quantity. So this is going to be less or equal, because x can be equal to 0. Then 1 over square root of x0 times magnitude of x minus x0. And now I can request that this should be less than epsilon, right? Square root of x0 is a fixed number. And so this would be equivalent to asking x minus x0 to be less than epsilon times radical of x0. Right, and so then I can use delta to be epsilon times square root of x0, And, oops, sorry. So I can use delta to be this. And so therefore, the function is continuous at any x0 between 0 and 1, not including 0. Now, why did I exclude 0? Because if x0 was included in this calculation, then I would be dividing by 0 here, and that's not allowed, right? So I have to treat the situation with x0 being equal to 0 separately. And so let's do that. Let's suppose now that x0 is equal to 0. So part B. Let x0 be equal to 0. Then we need to make, again, f of x minus f of x0 to be less than epsilon. So then f of x minus f of x0 is going to be just square root of x, right? Because in this case, we're subtracting 0 from square root of x, so we just end up with square root of x. And now we have to relate this to absolute value of x minus x0. x0 is 0, so we need to relate it simply to absolute value of x. So I want square root of x to be less than epsilon. And this would simply be equivalent, because x is positive. This is equivalent to, if I square both sides of the inequality, to x being less than epsilon squared, which of course trivially is the same thing as saying absolute value of x minus 0 is less than epsilon squared, right? Because x is a positive number, I can insert an absolute value sign here without any change. All right, and then what is my delta? Delta should be epsilon squared. All right, so that proves that the function is also continuous at 0. So then my usual question, is there a common delta that works for all x0 inside the interval I? Well, again, how do you choose a common delta? You have to find the smallest of all possible deltas here, right? And just by looking at what we got here, it doesn't appear that there is a smallest possible delta. Why? Because if x0 is not equal to 0, then my delta is equal to epsilon radical of x0, right? So the smallest out of those is going to be simply 0, right? Because the square root of x0, when x0 is between 0 and 1, the smallest number here is going to be 0. And so then it is irrelevant what delta is for x0 equal to 0, because that delta by default is not going to be the smallest. The infimum of all deltas is going to be 0. At least it appears so. However, the things are not necessarily how they appear to be at the first glance, and we'll show actually that there is a common delta, and we can find it by utilizing the fact that the function square root of x near x equal to 0 is small. And here is how I'm going to do this. So let's for now suppose that x0 is less than a epsilon squared for some a positive, and that delta is equal to a epsilon squared as well. Right? So I'm just forcing x0 to be very close to 0, right? Because epsilon is supposed to be a small number. And I'm choosing delta to be exactly the same as a maximum distance from x0 to the origin. Okay, so if that is the case, then x will belong to the interval from 0 to, right, so if x0 is a epsilon squared, and I go by delta towards 0, then I can get to 0 that way. If I go by delta in the other direction, I'm going to increase, I'm going to double a epsilon squared, right? So if I start at x0, which is a epsilon squared, and I go by, so actually let's make it less or equal, and I go by additional a epsilon squared, so it would be 2 a epsilon squared. And if I compute radical of x minus radical of x0, so in this case I'm not going to rely on the fact that the difference between two numbers is small, but I'm just going to rely on the fact that both numbers themselves are small. And so then by triangle inequality, we have that this difference actually must be smaller than square root of x plus square root of x0. And the square root of x, right, if x is between 0 and 2a epsilon squared, then this is going to be less or equal in principle. It doesn't matter actually. So what does matter is that we should have strict inequalities here, right? Because x minus x0 is less than delta, and so the sign is less here. So this is less than, what is the square root of x? It's less than square root of 2a epsilon squared, and square root of x0 is square root of a epsilon squared, right? So this whole thing, if I take out epsilon squared, is going to be equal to square root of 2 plus 1 times square root of a times epsilon, right? Square root of a is a common factor. Square root of 2 plus square root of 1 I can factor out. Epsilon factors out as well. And the goal, of course, is to make this less than epsilon. And how can I make this less than epsilon? Dividing both sides by epsilon of this inequality tells me that I have to have square root of a, which is less than 1 over square root of 2 plus 1, or a that is equal to 1 over square root of 2 plus 1, the quantity squared, which is 1 over, if I factor these things out, then this is going to be 2 plus 1, 3 plus 2 radicals of 2. All right? So that means that I can select a in such a way So if a is equal to 1 over t plus 2 square root of 2, if I select x0, which is smaller than this number, then I make delta equal to the same number, as long as x minus x0 is less than this delta, then I can guarantee that square root of x minus square root of x0 must be less than epsilon. Okay, so then what have we got? So therefore, if x0 is less than a epsilon squared, we have delta equal to epsilon squared divided by t plus 2 radicals of 2. If x0 is larger than a epsilon squared, we can employ the same computation that we did here, right? So in this case, delta is going to be epsilon radical of x0. So delta is epsilon square root of x0, and if x0 is equal to 0, then delta must be epsilon squared. Right, and so what do we need to do? The common delta, as we discussed before, is the infimum over all possible x0 of deltas, right? Deltas in general depend on x0. And so what is the infimum of these numbers that we got here? Well, infimum, we have three constants, this constant, and this guy, who in general will depend on x0. But it is epsilon times square root of x0, so the infimum of delta in the middle. So note, and let's put delta of x0 in all of those. So if x0 is larger than a epsilon squared, then the infimum of delta of x0 is, I just need to plug in the smallest possible x0, so that would be a epsilon squared. So this should be epsilon times radical of a epsilon squared. So this is square root of a times epsilon squared, right? So let me make sure that this is right. So if x0 is that, square root of a times epsilon squared indeed. So the smallest of these numbers in the middle is square root of a times epsilon squared. And then I have to choose the smallest out of three numbers. This one here, this one, and that one. So delta is equal to the minimum. And by the way, square root of a is square root of a is 1 over square root of 2 plus 1, right? So this is 1 over square root of 2 plus 1 times epsilon. So it's a minimum of epsilon a times epsilon squared. epsilon square over 3 plus 2 radicals of 2, epsilon square over square root of 2 plus 1, and then just plain old epsilon square. And which one here is the largest, is the smallest? Certainly not epsilon square. Epsilon square divided by square root of 2 plus 1 is actually larger than this number, right? Because 1 over 3 plus 2 square root of 2 was 1 over square root of 2 plus 1 squared. And so after all this pain and suffering, what we get is that the number is epsilon square 3 plus 2 radicals of 2. So that's the common delta. So in this case, common delta exists. And last thing for this example, let's look at the picture again. So in this case, we're working with square root of x on the interval from 0 to 1. And one thing that makes this different, for example, from the graph of x squared on the interval from 0 to 1, graph of x squared had finite bounded slope everywhere. Graph of square root of x has a slope equal to infinity at x equal to 0, right? So slope of f at x equal to 0 is equal to infinity, right? And before, when we encountered a slope that was equal to infinity, we always concluded that there is no common delta that you can find for your function on a given interval. However, in this case, even though the slope is equal to infinity, your function doesn't go to infinity, right? So the slope equal to infinity somehow is happening at a single point, in a sense. It's not, let me rephrase it slightly. So in our case, the slope was going to infinity, but it was going to infinity somehow fast enough to make the function go to infinity as well. In this case, the slope goes to infinity, but if you think about the derivative of f of x, it's still an integrable function, because even though the slope is very large, then the cumulative effect of a slope being very large is not sufficient to force a function to become infinitely large. And that is sufficient to ensure that the common delta exists in this case. So, however, common delta exists. Right, and we can draw the same picture here. So if I have a window of a size epsilon on y-axis, and I start shifting this window up and down, then the corresponding window on x-axis is never going to shrink to 0. Right, because if it did shrink to 0, then that would have meant that delta does not exist, right? And in fact, you can see here the difference with the case when the function went to infinity, when the derivative became infinitely large, right? In that case, for example, above, when we were shifting the window up, then the graph becomes steeper and steeper. So then the window of deltas shrunk to 0. In this case, if epsilon is moved to the region where the slope is infinitely large, for example here, we still end up with a non-zero range with non-zero delta on x-axis. All right, so let's now summarize our observations. So to summarize, common delta seems to exist on I if, all right, so if we look at this picture, what do we see? We see a square root of x, which is a continuous function on a closed interval from 0 to 1, right? And a common delta exists. In the previous case, number 4, f of x is still a continuous function, but it is a continuous function on an interval, so it was from 0 to pi over 2. Now it's an open interval because 0 is not included here. And in fact, I will not be able to extend this to a continuous function at 0, to continuous function on the closed interval from 0 to pi over 2. I can include pi over 2, but I cannot include 0 because I cannot make this function continuous at 0 just by modifying its value at a single point, because the function starts oscillating infinitely fast as we approach 0. So we have a continuous function, but the interval is not closed. In the case of example number 3, f of x is 1 over x squared on the interval from 0 to 1. Once again, looking at the graph, the function is continuous on an open interval from 0 to 1, or half open, including 1. But it cannot be made continuous at 0 because the function goes to infinity. So still we have a continuous function, but the interval is not closed. And for f of x equal to x squared, where we take x between, what was it, 1 and infinity? Between 0 and infinity. In this case, the interval, we can take it closed, right? We can include 0, there is no problem. Function is continuous, but common delta does not exist because delta will become smaller and smaller if I shift the window upward, and I can continue shifting it upward all the way to infinity because the graph continues all the way to infinity as x gets bigger and bigger. So there is no common delta here, and the function is continuous, and the interval is closed but not bounded, right? It has infinite length. And finally, example number 1, where we took a function interval from -1 to 1. Function was x squared. In this case, common delta existed. So what it appears to be true here, that if the function is continuous, so if f is continuous on I, and I is a closed and bounded interval. And so this suggests us that there is a theorem that we can try to prove. And so next I'm going to actually give a special definition to all functions like we are looking at here, where there is a common delta for all x0 on a given interval. So these kind of functions will have a special name that will be called uniformly continuous. And then the summary essentially formulates a theorem that we would have to prove. And the theorem says that if I have a function which is continuous on an interval I, and an interval is closed and bounded, then that function should be continuous.